Hey class, welcome back to our 7B Notes, which is our atmospheric pollution unit, focusing specifically on many secondary air pollutants. So today you can see we'll be discussing photochemical smog, thermal inversions, and acid rain primarily, along with some strategies for reduction of air pollutants in our atmosphere. Starting off with a quick recap of ozone. Ozone has three oxygen molecules that are bound together. We talk about ozone with this little phrase here, good up high, bad nearby. The reason for this phrase is to help us remember that up high, the higher layer of our atmosphere of the two we'll be discussing, is the stratosphere, versus the bad nearby, which is the troposphere, the lower one. So we live in the troposphere. The stratosphere is the next layer up. That's where we find our ozone layer, and that is where we want those molecules to remain to protect from the UV light that's coming to the planet. The troposphere ozone is dangerous because it is a harmful molecule to plants as well as human respiratory systems. So we'll discuss its formation and its role in the troposphere. Remember, CFCs are a man-made greenhouse gas, and they lead to ozone destruction or ozone depletion, or the thinning of the ozone layer, and that occurs in the stratosphere. So let's focus on this bad ozone, the bad nearby ozone in the troposphere. Tropospheric ozone is also referred to as ground level ozone, so you may just hear it simply called ground level, or even sometimes bad ozone. This really results as a primary pollutant and is harmful to plants as well as people. Let's talk about formation first here. So we have a little bit of chemistry here. You won't need to know the complex chemistry of this, but essentially what I'm trying to show you in Part A under primary pollutant sources is the combustion of fuel, particularly the combustion of gasoline, is going to release two pollutants here. Now, these nitrogen oxides can come from coal burning and other sources. Same as these VOCs can come from things like paints and in gasoline too. But ultimately, however these get into the atmosphere, they can react with sunlight and heat, which speeds up the reaction. So this is here to speed up the reaction. All right. And what's the reaction that we're doing? Well, essentially, without getting into the complex chemistry of it, nitrogen oxides have oxygens. And we're going to kick out free oxygen here. And a lot of the VOCs, things like carbon monoxide, also have oxygen, right? So we can remove oxygens from these molecules. And as there's more heat and sunlight, the more oxygens we can remove. And these free oxygens are going to want other oxygens to bind to. So they're gonna end up bonding with O2s, which is this here. Basically, here's our free oxygen. That's what we're pointing out. So nitric oxides, VOCs, heat and sunlight are going to release these guys. And then there's going to be some O2s floating around as well. And these oxygens are just going to make their way to the O2s, and then they're going to create our tropospheric ozone. So what is the problem with this? Well, the more pollutants we have in our atmosphere, the more likely we are to strip these oxygens from these molecules and form this ground level ozone at a higher rate and also in greater amounts. So ozone can degrade plant leaves. Directly has an effect on the cells of the plants that are going to allow it to do photosynthesis. So primary productivity is definitely reduced as a result of increasing ozone levels. The ozone can be a respiratory irritant to our lung tissue, as well as just affecting overall health. Eyes getting watery, burning, that kind of thing, itchy. But particularly for the respiratory system, it can be an issue. And then ozone, again, is highest in afternoon and summers. This has to do with the amount of cars that are present here. All right, so more cars, more of these molecules, and then the heat and sunlight are going to speed this reaction up, so it's going to get our ozone in higher amounts. Kind of twofold reason why we would see that higher in the afternoon and in the summers. Piggybacking off of tropospheric ozone is photochemical smog. Smog is a kind of a more general generalized kind of term for additional pollutants that start to be formed from a very similar process as tropospheric ozone. And in fact, tropospheric ozone is part of photochemical smog. Smog is a secondary pollutant that forms this really thick brown haze we can see in the background. We see smog very typically in urban areas due to the high number of cars. Also areas that have very dry, sunny, calm winds, poor airflow circulation, or just we really don't get a lot of strong winds coming through, like a mountainous area or a valley, can form photochemical smog at a much faster rate and have more chronic problems with this. Essentially, the sources are very similar to ozone. We have our NOx's, our nitric oxides, our VOCs, and then this is where smog is a little different than ozone because it's the other hydrocarbons that start to react with, again, heat and sunlight. So smog and ozone formation are very, very similar. Just remember, smog kind of has more stuff in it. Ultimately, some of these other pollutants that are formed are things called PANs and aldehydes, and these PANs and aldehydes combine with ground level ozone to form smog and nitric acid and a bunch of other things. So smog is a bigger mixture of pollutants, and that's the easiest way for me to distinguish from ozone, because here's ozone formation. We talked about that. That's one of the things. But then we get our hydrocarbons that are going to form these PANs and aldehydes. That's the second thing. And then we also end up with nitric acid, and we'll talk about that formation in a bit. So all these pollutants make up this mixture we call photochemical smog, with the chemistry behind what's happening in the nitric oxides and the formation of the ozone is all the same as we just discussed in the previous slide. Again, issues with this stuff: eye irritation, lung issues, just not a good thing to be around chronically in terms of human health. Acid deposition is the next secondary pollutant we'll be discussing. This is a generalized process here, and just a quick review of pH and what we mean when we say acid or acidic. Basically, what we're looking at in our pH scale, 7 is kind of neutral, right? Seawater, salt water, we like closer to 8. And then anything that's acidic is a lower number. So lemon juice is 2, stomach acid 1, battery acid 0. So just recall that when we use the pH scale, that's what we're referring to. The general overview of acid deposition is that these acidic gases, things like sulfur dioxide and nitrogen oxide in particular, will come up. They'll be carried by wind. They'll combine with water vapor. They'll come down in the form of a liquid, or like rainfall or sometimes snowfall, and that will become more acidic as a result of combining with the water. And we'll go into the detailed chemistry here right now. So when we say deposition, we can refer to wet or dry deposition. Wet deposition can be acid rain, snow, sometimes fog, acidic fog. And then dry deposition, acidic gases and dry particles can settle on the soil as well and decrease soil pH and cause it to be more acidic. This is a result of primary pollutants, sulfur dioxide, and our NOx's, our nitrogen oxides. The secondary pollutants that are formed are sulfuric acid and nitric acid primarily, and that's what we'll focus on in the diagram here. So looking at our primary pollutants, those will be in yellow. We have sulfur dioxide and nitrogen oxide. Sources from automobiles, nitrogen oxide, that's the number one source. It's combustion of gasoline, and sulfur dioxide is coal-burning power plant. So they get up into the atmosphere. Then what happens? Well, they're going to react with water, and those two components primarily will produce secondary pollutants of sulfuric acid and nitric acid. So looking at this, we really have our pretty basic chemistry here, right? We have H2O plus, then it could be plus sulfur dioxide or plus nitrogen oxide, or sometimes both, right, if we have this in the atmosphere. And that's going to form these acidic molecules, and when it rains or snows, that settles down onto the ground or into our waterways and causes a decrease in pH, resulting in a more acidic environment. So why is this bad? Why is acid deposition a problem? Well, decreasing pH, while however small, if we're supposed to be more neutral, even if we decrease it by 1 pH unit, so from 7 to 6, or even below from 6 to like that 5.6 mark we talked about, the pH can cause issues. Particularly decreasing pH can affect aquatic organisms in a lot more significance because they're surrounded by this decreasing pH all the time. If we change the pH of a stream or a lake, what ends up happening is the embryonic development of a lot of fish and amphibians can be stopped completely, could destroy the eggs, could cause birth defects in these organisms. We also get yellowing of tree leaves and chlorophyll loss. Same thing can happen with pine needles, and we see like waxy coating. The cuticles can be slowly stripped away from chronic acidic deposition, which affects its ability to do photosynthesis, which ultimately causes big problems on a large scale. If it's really chronic, we can lose entire areas of forest. The acidic pH of the acid deposition can also kill the symbiotic bacteria and fungi, particularly the ones that are in the root systems that help these plants, move nutrients and get nutrients out of the soil, and also put nutrients back into the soil. The other thing that the acid can do is help leach aluminum out of the soil and into streams. That is harmful for the fish in particular and their gills, which can affect their well-being. It also causes problems with stonework and buildings, so that can damage and erode artwork, stonework, or just our architecture over a long period of time. Acid deposition is regional, so we need to understand that this is not this is something that can affect local areas and definitely moves downwind. So we see a consistent pattern or trend with the air currents from areas that have high sulfur dioxide or nitric oxide output, and then the areas downwind of that are the ones that are suffering the consequences, not just the immediate area. So that's important to know. One of the remediation effects we can use is calcium carbonate, which is found in limestone to act as a buffer. So if waterways are too acidic, we can add limestone to it. If the bedrock is already just naturally a limestone type bedrock, that tends to kind of naturally buffer out the impacts of the decreasing pH of areas that are affected. We also have another unique event here in our secondary pollutant section called a thermal inversion. Essentially, thermal inversions are these abnormal temperature inversions where we get a flipping of the typical temperature gradient. What we usually see is warmer air near the surface, and then as we move away from the surface of the Earth, away from a city, up into the atmosphere, it gets cooler and cooler. With a temperature inversion, we get a little bit of a shift in density, and essentially what happens is the air by the city is going to cool more quickly at night, and as it cools more quickly, we get this warm inversion layer that sits on top, and essentially this inversion layer creates almost like a lid or a ceiling over top of the city, which doesn't let things like smog or other air pollutants escape. And what happens is it just gets kind of trapped near the city. Again, this is very similar to what we talked about with smog. The areas that are subject to thermal inversions tend to be cities, and cities with low-lying areas surrounded by mountains, slower wind currents. Those kind of things are going to allow these thermal inversions to occur more often. And again, it's a result of the more rapid cooling of the ground near the city, which creates this density differential in the air sitting over top. The final bit is our reduction of air pollutants. There's a lot here. Understand that each one of these has their place in specific air pollutants and how we're trying to reduce them. First off, the Clean Air Act is something we put in as legislation in the United States, and there's been many amendments and revisions to it, but ultimately regulating emissions and setting air quality standards for public health is something that was addressed as a specific need, and that continues to update. Right now we have 6 criteria air pollutants primarily, but that can always be something that changes. The Montreal Protocol was a big one. We talked about ozone depletion, the stratospheric ozone layer. The Montreal Protocol stopped CFC production with a goal of zero production by 2000, which was met for the most part, and it was kind of hailed as a great environmental success story. We replaced them with HCFCs. These are less ozone depleting substances, and the goal is to phase those out in 2020, and it appears that that goal has been widely established because the HCFCs were still pretty powerful greenhouse gases. And they were still a little bit ozone depleting. The CFCs now replacing with HFCs, the hydrofluorocarbons, are much better for ozone layer, but we still know that it's a powerful greenhouse gas. So it's kind of solving one problem out of the many that we have, but it's still a great step forward in terms of rallying together for legislation that is leading to environmental success. Other things that we put in terms of managing air pollution, things like scrubbers and electrostatic precipitators, are going to be things that are going to reduce pollutants and gases in the gases from the exhaust, whether it's a factory or a power plant, anywhere where there's particulate matter coming out or other pollutants that can be removed by these types of structures. Vapor recovery nozzle, you may have seen these at gas stations. They're becoming more common in recent years, but basically it prevents fumes from escaping while fueling vehicles or reduces the amount of VOCs that are basically coming off of the gasoline while you're pumping. And then finally, catalytic converters are in all our vehicles. These are something that have been really important in reducing the amount of nitrogen oxides and hydrocarbons that are coming out from our exhaust. So it's definitely helped to reduce the load of those air pollutants from the tailpipe.